Okay. So last time, and we talked about the broken linear search, right? We talked about how we shouldn't, here it is with a while loop. We talked about how we have to be careful because we only know, we know we found what we're looking for when we find it. But we cannot conclude that the thing we're looking for isn't there until we've looked at everything. That's why in here, it says if the thing, imagine the first time this loop runs, count as 0. If the thing isn't, like if this condition is false, if the string at 0, if the first letter isn't the thing we're looking for, then we immediately return false. All this function will do, despite having a loop, all this function will ever do is tell us if the thing we're looking for is at the first index. Because as soon as a function sees a return, it stops executing its code. So the correct option is to move the return outside the while loop. Only after we've looked at everything. I mean, it doesn't have to be the while loop, it could have been a for loop. But only after we've looked at everything, only after that loop finishes, and that loop will only ever finish if it never returned true. So if that loop ever finishes, that means we looked at everything, and we never returned true, meaning it's not there. So here's the underlying idea. You got to remember, I'm looking for x in a sequence. So here's an example, right? I'm looking for x, and we're storing, we get some list or some collection of things. Like, although the collection of things is stored in the computer, I mean, the code doesn't know what's in there until it looks at it. And it can only ever look at one thing at a time. So when it starts the search, it's got this list or this collection of things where it doesn't know what's in there. We have to look at each thing. So if I look at the beginning of the sequence and see the value x, I'm done. It's there. I can stop looking. But let's say I was looking, all right, I can only confirm that something's not there. What does it say? However, if I was looking for some other value y, I can't confirm that it is or is not there just by looking at the beginning element, or second element, or third element, et cetera, until I find what I'm looking for, unless it's not there. So this may have been where the question came up. If I had a list of 10 things, how many things would I need to look at, best case scenario, to know if the thing I'm looking for is there or not? One, the first one. If it's the thing I'm looking for, great, we're done. What's the worst case scenario, though? How many things would I need to look at? Couldn't really hear. People whispered to themselves. I can't hear that. 10, right. If I double it to 20, how many things would I have to look at? If I multiplied that by 5, how many things would I need to look at? 100. This is a linear time algorithm, which means, and you have to be careful about what this means, and we're going to hit this idea harder a little later in the semester, and a lot more in 162. But what this means is the amount of work this algorithm takes grows linearly with the size of the input. And if that sounds intimidating, it's just because it's using mathy words. All it means is if I double the size of the input, I have to do twice as much work. If I quadruple the size of the input, I have to do 4 times as much work. As the input grows, the amount of work I have to do grows the same way, more or less. That's what that means. But there are algorithms out there that are, there are algorithms out there that won't be linear. They might be quadratic, meaning if I double the size of the input, I actually have to do like 4 times as much work. It grows at the rate of the input size squared. And we'll see these a little later. Now I'm going to throw some string trivia at you. Well, okay, here, actually, this was an activity. We're not going to do it. But this was a modification on the linear search where it wasn't return true or return false. It was return the index. If it exists, return the index of the thing you're looking for. Now, if you're doing with a for loop, this is a little tricky. If you're doing it with a while loop, it's pretty easy. Because a while loop, if you're using a while loop to iterate over the contents of the collection, chances are you're going to have like a counter to keep track of the current index of the thing you're looking for, right? So if you find the thing you're looking for, just return the index. If it's a for loop, you don't actually have access to that index. All you have access to is the current character that you're looking at. So it's harder to return the index. There's ways to do it, but it's a little trickier. Anyways. And often what we'll do here, see, if the character does not exist within the string, return -1. So here's the problem we have. This function's supposed to return an integer, which represents the index that the character exists at. But what do you return if it's not there? Well, what we do often in a situation like this is you return what we call a sentinel value, which is just a fancy way to say we return a special value that means something to the programmer. Let me show you what I mean by actually doing this example here. Let's go here. I'll just copy this one and alter it to fix it. Maybe we'll make this index. There, I think that'll do the trick. If I return, like the reason -1 is important here. Now, it's not that it's -1. It could have been -2, it could have been -3, whatever. But I can't return a positive integer to mean that it wasn't found, because a positive integer could correspond to the index in which that character exists at. So I need to return a value that's an integer, but really wouldn't make sense in the context of this function if it was, working properly. Meaning, if I saw a -1, and I asked, if I asked the function, tell me the index that this character exists at, and I see -1, that doesn't really make a lot of sense. So it's fair, it's safe to use that value as the sentinel value. So here, if I call this function, we see a 2, right? Because A is at index 2. If I look for like an x, we see -1. Because x isn't there. So this would be an example of a sentinel value. Often programmers will also do this, is they will there. So now we use a constant to mean the sentinel value, so now it's even more clear. A -1 to a programmer, that in a context like this would make sense. It's a sentinel value just by experience. But there's nothing wrong with making your code that much more clear by adding a constant to be like, oh, well, the -1 means it's not found. Any questions about that? All right. All right. So here's some string trivia. I'm going to blitz through this. This is obviously not exhaustive. The point of me showing you this is so that you're aware of these things, and if you need to use them later on, you're aware of them so you can go back and look at this or look them up on your own. It's better to know what you don't know than it is to not know what you don't know. So I'm doing that right here. So first and foremost, both of these are valid. Both are strings. I mean, the difference is the top one uses double quotes and the bottom one uses single quotes. Now, does anyone know which one I would say is the better option to use? The first one. Why? You know it's the first one, but you don't know why. There's a couple of reasons, and to be clear, if you use single quotes, there's nothing wrong with it. But the reason double quotes I would say is a little better to use is because, one, it's more consistent with other programming languages. The other similar, very popular programming languages use double quotes for strings. Single quotes actually mean something different. It means a single character. So this is a little weird here. Another benefit, if I'm using double quotes, I can use a single quote within the string, where if I tried to do, like, look what would happen if I, like, that's not going to work because it's expecting the single quote to, like, end the string, right? So it's a little nicer there. Now, if you really wanted to use single quotes, there is a way. You use this escape character. Well, you use a backslash, which means, here, I can go print B out. Like, this backslash has special meaning depending on the context. It basically means, like, I know it's a single character, but I don't, a single apostrophe or quote. I just don't treat it like one as if it's like the Python syntax, just pretend it's part of the string. But then you might say, but what if I really wanted like a backslash to be there? Well, you can do that by backslashing the backslash. There's a lot of stuff like this. End of the day, though, double quotes is a little nicer, I would say. Even within the course notes, you'll find examples of where I use single quotes, but it really doesn't matter. But if you're ever sitting there going, which one should I use? Use the double quotes. That's a little better. Did you have a hard time finding parking? No? Because I couldn't find parking. That's why I was like a minute late. There was no parking. Jeez. This one you already know. Concatenating strings. You add strings together. You stick them together. You can multiply a string with itself to repeat it several times. Cool. You can convert an integer to a string, which I'm doing here. I'm kind of showing here where I'm saying, what's the type of 1? And printing it out, we see int. Take the 1, convert it to a string, ask what its type is, print it out. Well, it's a string. Yeah. You can have empty strings, which sounds weird, but it's pretty important, actually. Let me show you what I mean. See, I've got a string, but there's nothing in it. And you might be like, well, that's basically like none, but it's not. No, it is still a string. I can ask the type of A. It's a string. I can ask the length of A. What do you think the length of A is going to be? Yeah, 0. But it is a string, so that's kind of neat. Oh yeah, we have these special characters here. /n and /n /t, and then I'm using the 2 here again to show you that I can write it if I want. See, we use /n. Who wants to guess what \n does? Come on, you can look at the output and guess. A new line, right? And if you're wondering, well, why do I need that to make a new line? Well, what button do you press on your keyboard to make a new line? Well, that's easy. You just press enter, right? So why do I need that? Oh yeah, that's not going to work because if I hit enter, it's not going to know. So in order to like embed a new line into a string, you use /n. Who wants to take a wild guess what /t does? Tab. Yep, exactly. Right? Now, you could say, I could just tab it here and it'll still kind of do it. But This way I'm actually like embedding a tab character into it where the other one just added a bunch of spaces. So that's kind of neat as well. Now actually be warned, raise your hand if you're using a Mac. Okay, so if you're using a Mac, the /n is like fine. Now this will be fine because we're running this on Google's computers, not on your computers, and the languages now are pretty okay with this. But back in my day, if you're using Windows, it's not /n to make a new line. Does anyone know what it is? This is some hard trivia that I don't expect anyone to know, but I'm curious. No, it's /n/r, or /r/n. I don't think the order matters. And there's a reason for that. The n means new line. The r means carriage return. And so there's actually a lot of, I said this in the other section too, I often think to myself, it would be a lot of fun to make a course on kind of like the weird history of computers and computing, where you learn about like there's a lot of things that exist today. There's a lot of conventions we follow, a lot of rules we have to follow. There's a lot of things that exist that are kind of weird, but there is an explanation as to why they exist. So one of these examples is the /n/r. Who here has ever used a typewriter before? Really high, I want to see. A whopping 1, 2, 3, 4, 5 people. Who here is at least familiar with a typewriter? Okay, everybody. Now, in case one of you is lying because you didn't want to feel left out, the typewriter is that whole very mechanical device to write things down. You know, you press a button on the typewriter and that arm goes whack and it hits the page and puts a letter on the page, right? Now, what's interesting about a typewriter is, I mean, you go back a little while ago, if you wanted to print something, you could like hook up your computers to these typewriter type things, and that's how you would print. Long time ago. But what's interesting about it is, like on a modern printer, the print head moves, right? If you're printing something, the thing printing moves across the page, right? But on those typewriters, it was different. The page moved, okay? So the thing that, like the target that the letters went was always on the same spot, but it was the page that moved along instead of the print head, okay? Does that make sense? Now, who remembers what you'd have to do? For those of you that used a typewriter, what did you have to do when you got to the end of the line? You know, you're writing, and it goes ding, right? What do you have to do? I'm seeing people go, yeah, you go, that's the carriage return. You got to move. You can't just go to a new line. You have to move the page back, right? And go to a new line. And it's because of that why we have /n/r. You had to carriage return and you had to new line. Those two different characters, because a new line is a character and this carriage return is a character, had special meaning for these printers. When the printer saw that carriage return, it knew it needed to move the page back. Cool, right? Anyways. Say it's cool. Say, yes, it's so cool. So cool. Yeah, there you go. See, I told you. All right. Now, here's something interesting. Now, remember I used the word primitive type, right, before? And that's a word we would use for like your integers, your floats, your booleans, and even an individual character, classically speaking. And what we like about those is those fit nicely into a chunk of memory that we're really happy with. Now, take a moment and think. Anything you have stored on your computer must be representable physically as low voltages and high voltages, which we like to talk about as zeros and ones in the digital world, right? So we say zeros and ones. Any picture, any song, anything at all that you're looking at on your computer must be representable by zeros and ones. Now, when we have a picture, how do we convert that picture to zeros and ones is a big question. That is the encoding. Somehow we take the picture, we turn it into zeros and ones. Somehow we take the sound clip, we turn it into zeros and ones. Okay? Now, that means anything that we can represent can be encoded into zeros and ones. It has to be encoded. But then, if I gave you a string of zeros and ones and said, what is that? If I said, what was it? Hold on. I did this last time. I can't remember. If I said hold on. Everyone close your eyes for a second. Yeah, okay. 0, 1, 1, 0, 0, 0, 0, 1. Right? If I said that, no, that's, yeah, okay, 0, 1, 1, 0, 0, 0, 0, 1. And I said, well, what is that? You can't answer the question because 0, 1, 1, 0, 0, 0, 0, 1 is an encoded value. It has meaning. But in order for you to decode what that means, everyone make sure you're paying attention. What I'm telling you right now is a big deal. In order for me to tell you what that means, I need to know, well, what was encoded? Was it an image? Was it a sound file? 0110 0001 has meaning only if I know how to decode it. Something was encoded into those zeros and ones, but what was it? Well, in order to know, I need to decode it. So, 0110 0001, if I ask you what that means in terms of letters, what's the answer? Who knows? It's a letter. It means something as a letter. No one knows? Come on. No one wants to take a wild guess? It's the letter A, of course, obviously. It's actually a lowercase a. But if I told you, now this you might know if you cheated and didn't close your eyes. If I told you, no, never mind, I messed up. Don't decode it as a letter, decode it as an integer. What number is that? Oh, everyone was good and closed their eyes? 0110 0001. Come on, you know what that means. Well, it's 97, obviously. So what's neat here is those binary strings, if I have a binary string and I say decode it as, the computer will decode it as whatever. Let me show, has anyone ever accidentally, here, okay, this is too big. I need some arbitrary file. I need something small. Give me a moment here while I look for something, because I'm going to show you something that I think is kind of neat. Now, where did I restore that to? Perfect. Has anyone accidentally opened up a file and you saw something like this before? Yeah, it's because I opened up a video file with a special encoding, an MKV, but I said, decode it as if it's text. And the computer said, okay, here you go. But of course that's nonsense, right? Some of those things you can recognize. Look, there's an N. There's a regular old N, an uppercase P, a lowercase a. There must have been a 97 over there. There's a lot. It looks like garbage. Well, this is because you had some zeros and ones encoded. You had video encoded as zeros and ones. And instead of trying to decode it as a video, which would work, I'm trying to decode it as text. And the computer's happy to do it. It's just, it's nonsense. Yeah?
This is going to sound kind of stupid, but this isn't some higher level of programming.
Say that again?
As a kid, I always thought this was what, when you coded, it converted to this.
When I coded?
The actual code.
Well, so it's, so kind of actually.
At least you could type, A, BX7 plus 4, whatever, that would somehow work.
Now, if you did that, that wouldn't work, but you could. Meaning, if I can, let me put it this way. If I can encode a video into zeros and ones and read it as text, that means I can encode text and read it as a video. Meaning it is possible to write a whole bunch of nonsense and then play it as a video. Now, don't try, you're wasting your time, but you could. Because it's all about, those are just zeros and ones. What they mean, I can't tell you what they mean until you tell me how to decode it. Here's the computer trying to decode it as zeros or as text. So this is all to say, I can actually convert a character into its number. And I can convert an integer into its character, which is kind of neat. Now, here's the big one. Of all the trivia I want you to see, let's say I want to read some input, do something to it, and then print it out in a string like this, right? Okay, great. I'm going to run this. 5. It's not going to work because I got to convert it to an integer, or sorry, into a string. Okay, so I'll convert it to a string. So now I do it. I'll do 5, 10, and I see, oh, not A. I want to print S. We see 10. Oh, that should have been B. My goodness. Oh, and I forgot a space. My goodness, this is frustrating, right? How many of you have done something like this? And then I say, yeah, and then on the next line you want it to like line up nicely or something. Well, suffer no more. I'm going to show you something called F strings, formatted strings. F. You have to put this little F in front of the string. And then you can say, you know what? I'm just going to get rid of this part. So now with these F strings, I can actually embed the variables right into the string. Instead of having to concatenate strings, making sure everything is the correct type, I could even add, if I wanted, I can even throw in arithmetic inside there as well. It's a little easier. I'm very aware of where the spaces are. So F strings make it a lot nicer to have these nicely formatted strings, which is really great. And you can actually do a lot more with them because, let me show you this example. Here, I'm going to get rid of some of the text to make it a little. There's even more stuff I can do. I could do this like :2f, which looks like nonsense, but there's a lot of little like things like this that says, yeah, that's a float, but I only want you to show 2 decimal places. And notice that it actually rounded for you, which is kind of neat, right? I said, show me 2 decimal places, and it rounded the 789 to 79, which is awesome. So it kind of took care of that for me, which is really nice. And you can even do like alignment here. Like if I wanted to print out like a grocery bill, right? Let's say I'm making like a receipt and I want to print it out. That's probably how I'd do it, right? You know, $10.95, $1.10, $123.45, and I print it out. Suddenly I've got, you know, the decimals don't line up. I want the decimals to line up nice. I've got like 110, but it's only showing 1.1. That's annoying. I want that, you know, I want it to be 10, right? So that's kind of annoying. Well, struggle no more. There's a lot you can do. Here I wrote in the literals. These, of course, could be variables. What this says, so first of all, notice there's a lot of white space to the left. But this says take up a total of 8 characters at max, and I want you to make sure you're including 2 decimal places. So anyways, it's beautifully formatted compared to the other ones, right? There we go. So here's a nice way to format your strings. Like I was saying, this is obviously only scratching the surface. I'm only showing you this so you're aware of what's out there, so you're aware of what you don't know, so when you want to know more, you can go look it up. If you weren't aware of this, you know, good luck finding this, right? So I'm not expecting anyone to be an expert after this blitz right now. And besides, even if you were sitting here going like, I wish you showed me more, you're thinking about programming wrong. If you think you could sit here and listen to me and memorize everything I'm going to tell you, you're crazy. No. All you need to know is, something exists, and if and when I need it, I just go look it up. That's how every programmer does it. Don't try to memorize this stuff. You're going to lose your mind trying to. You know, if there's something you use over and over and over and over again, fine, you know, you'll eventually memorize it. But for the most part, especially for like more obscure functions and methods and things that you can do like this, you're not gonna memorize these things. You just are gonna have to look them up later for when you need to use them. And that's the correct way to program. Any questions about any of the string trivia stuff before I go to the next little bit? All right. Now, I'm going to briefly talk about objects. Objects are the topic of topics later in the course. There's several of them that are specifically on objects. We're going to learn how to make our own objects. But right now, I want you to be aware of objects. And there's some terminology and ideas that we're going to hit right now. It's going to be at a high level, but it's going to be important that you understand them at this high level going forward. So when we're talking, and everything I'm about to say is I'm going to be speaking like really like traditionally speaking. In Python, there's 1001 asterisks. A lot of modern programming languages have a lot of asterisks attached to this stuff, but these languages try to pretend that they're acting the way I'm describing, just because this is how they work traditionally and everyone likes this. So you've got your integers, you've got your primitive types. You've your integers, your floats, your booleans, your individual characters. You know, they're nice, they fit into memory really good. But then you have things like strings, right? And we saw strings were tricky because how much room do you need for a string? Well, it depends on how big the string is, right? An integer, it could sit in one of those seats. A string, well, if it's got 10 letters or 100 letters, the one with 100 letters is going to be bigger, right? So strings are funny. So this is where, like, a string is an example of an object. An object is like a catch-all term for things like strings. Not your integer, not your primitive types, not your floats, not your booleans, not your individual characters. So strings are they're objects, they're different. And what's neat about strings is strings have properties, and they also have functionality associated with strings. But we call these things methods. They're not the same as functions, but they are very, 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 very similar. For example, here is a function, print. That is a built-in function that was given to you. If you give it a string, if it gives you some argument, it'll try to print it out, right? Then we wrote our own function like character is in, right? We wrote that function. That function takes 2 arguments, and it returns a Boolean, right? Those are functions. This one took 1 argument, although actually print can take arbitrarily many. You can keep adding commas and add as many arguments as you want, and it'll print them all out just with spaces. This one here, it takes 2 arguments because we programmed it like that. But here's what I want you to do. Well, if you could just follow along with me, actually, just for sake of time. Let's go here. Sum string equals. Great. Does everyone agree that's a string? Yeah, cool. So check this out. I wrote the variable name, and I pressed dot, and I got this pop-up. And all of those things there that you see are methods associated with strings. Here, let's change this to that. There. So what happened? I made a string called this is a string. I printed it out. That's the first print. This is a string. And then I said print some string dot capitalize. And you know what? Maybe we'll like it a little bit better if we do like this. There. First of all, what do you think SumString.capitalize did? By looking at the output, what do you think? Yeah, right? It uppercase, it made the T uppercase. It capitalized the first letter. What else we got? There's a lot in here. Split. Who here has used split before on strings? Yeah, that's a method. Now that method actually took an argument, but you didn't have to add one because default it's split on spaces. But let me ask you something about split. That's a method. But you called the method on a specific string. The string you read in his input for Caddis, you said my inputted string dot split. And it gave you back the split string. Here's another one. Just makes the whole string uppercase. Methods are functions, but they're associated with a specific type, a specific class, like this is a method for strings. And when you call the method, you call it on a specific instance of a string. I called it on a specific string, on the string stored in some string. So that's actually the implicit argument. What I mean by that is, imagine a world, if this was like a function, if it wasn't a method, let's imagine there was an uppercase function, and it took a string and it gave you back the uppercase version of it, right? I would call it like that if it was a function, right? There's a function called upper. It takes a string, and I want it to return that string, but uppercase, right? Well, that function doesn't exist. But there is a method for strings that does, and you call it like this. Even though upper never took an argument. There is no argument in those parentheses, right? You agree, there's nothing between the parentheses at the end of upper. It still acted on a value. And that value was the instance of the string that it was called on. The string stored in some string. That is the implicit argument, meaning although I didn't actually give this method an argument, it's acting on the string it was called on. You've already been using split. Split splits the string you call it on. So that is a method. If this one didn't take an argument, some methods can take arguments. Let's look at some of these. Count. Let's see what count does. Return the number of non-overlapping occurrences of substrings, sub in string. So I can ask for is. Count of is. Well, there's two. There's an is here, and there's an is here. So this is an example of a method that took an argument, but it still used the implicit argument. The instance of the string this method was called on. The one that it was like dotted, right? Some string dot method. Just like before, if you're thinking to yourself, just like this, just like I showed you, all right? A string dot upper versus upper a string. If you're wondering, how was I supposed to know that upper didn't exist as a function? I was just supposed to magically know it was supposed to be a method. You're not. You're not magically supposed to know it. No crazy person is going to memorize this stuff. The only way you're going to memorize it is if you've been using this method a lot for whatever reason, fine, you've memorized it. But after today, a month from now, I'm not going to sit down and say, tell me all the methods associated with strings. No, that's crazy. No, instead, you look them up later if you need it. You go, yeah, so how I remember what? You don't. Things will stick once you get enough practice. In the meantime, you go make a string uppercase in Python, and then you see, oh, just call the upper method. Great. Do they have an example so I can see how it's used? Oh, perfect, they do. Great, awesome. That's how you do it. If you're thinking, oh, I'm so annoyed, how am I going to memorize all this stuff? You're doing it wrong. Stop trying to memorize this stuff. It ain't going to happen. All right, we'll end here.